like Ray Core to facilitate scalable, high-performance data processing, such as working on the data plane, and then working on some libraries like Dask on Ray and Ray Datasets. And I really love working on data-intensive distributed computing. It's a lot of fun. So first, quick overview of the talk. Scaling machine learning tends to be pretty hard, and there are also some non-intuitive bottlenecks that I'll get a little bit into. Ray error, in general, makes this scaling pretty easy. It's usually like a one-line config change to go from a single node to multi-node training and batch inference. Ingest, and I'll define ingest in a little bit, is a pretty common bottleneck once you start moving to larger data and larger cluster scales. And Ray Datasets solve some of these ingest bottleneck problems, and we'll do a little bit of a deep dive into how we solve those problems. So first, scaling ML is pretty hard. Your typical ML pipeline might look something like this. You've got some data loading and preprocessing with some of these familiar single node libraries, such as Pandas and NumPy, or distributed libraries like Spark and TensorFlow. And then you basically take that preprocessed data and ingest it into a trainer, or take that preprocessed data and move it into your batch inference call. And when it's on a single node, this ends up being pretty efficient. The data is all just transferred within memory. That exchange is usually not much of a problem. You don't have to worry about it. Unfortunately, we can't always stick to a single node. Eventually, your machine learning pipelines must scale as your data scales. And there are two big drivers. Either your data doesn't fit into the CPU or GPU memory of a single node, or your machine learning pipeline ends up being too slow if you just constrain it to the hardware resources of a single node, or if it's just to churn through a large data set sequentially on a single node. Can just, as a baseline, take too long. So one of the most common solutions here, pretty much like the canonical solution, is distributed data parallel training and batch inference. And so for training, you parallelize training across multiple GPU workers. And how that works is you have a couple of trainers, usually one trainer per accelerator, and you might have multiple accelerators per node. And you then assign a shard, a disjoint shard, one disjoint shard per trainer. And then you do a gradient all reduce at the end of each training step to synchronize the gradients. And so this is like the classic like data parallel distributed training paradigm. And for batch inference, it's kind of a very similar model, much simpler, thankfully. You can parallelize batch inference across multiple GPU workers. Here, it's the same sort of like sharding or partitioning scheme, but this is embarrassingly parallel. You don't need to have a gradient sync. It's all just a forward pass through your model. Perform batch inference in parallel across a bunch of workers, and then usually like store the output to persistent storage or feed it into another system. But in either case, distributed data parallel is kind of the paradigm that solves this data scale problem. And for your typical ML pipeline that we talked about, trying to go from single node to multi-node, usually it would end up looking something like this, where you have a Spark cluster doing some pre-processing. You have something like Horovod and TensorFlow to do distributed training. And then you usually have something like TensorFlow, like a Pandas, like a Python UDF and Spark to do TensorFlow batch inference. Or maybe you're using something like Dask or SageMaker if you're on AWS. And that's how you try and scale out your batch inference. There are a few difficulties with this. It's multiple disparate systems that you're stitching together. So you're having to manage multiple separate types of clusters, and it's also difficult to extend, especially once you start hitting performance bottlenecks, and we'll get to that in a little bit. There's inefficient data exchange between these systems because you're having to persist data to storage when going between pre-processing and training. There's no shared data plane, in-memory data plane like you had on a single node. And it's also difficult to keep those accelerators saturated as data scales, and as these accelerators continue to get faster, they're getting hungrier and hungrier for more data. They are very hard to satiate. So one possible solution to a few of these problems, in particular the keeping your accelerators saturated, is you try and pipeline that Spark-based preprocessing with training. And this usually looks something like this, where you have this separate coordinator microservice that is in charge of coordinating the pipelining, where you're trying to overlap that Spark-based preprocessing for example, for a future epoch with the training on a current epoch, or maybe even like within an epoch, you're doing the Spark-based preprocessing on a subset of data while like we're already training on an earlier subset of data for that epoch. And this is generally the protocol here, and you usually have to use external storage to transfer data between preprocessing and training. And there are a few issues with this. Well, first of all, it's pretty difficult to orchestrate. You've now gone from two disparate systems stitching together to now your own bespoke coordinator microservice to try and orchestrate this pipelining. So that's a little bit difficult. And then you also have to still materialize data to external storage. So you're always having to write out to external, like remote store, like S3, or maybe you're using something like HDFS. In either case, it's both expensive to write to that storage, and then you have to serialize it and deserialize it, which ultimately both takes time and also takes resources. So how are we trying to solve this problem in Ray? How can you scale ML pipelines using Ray? We have this high-level unified ML toolkit called Ray Air, which I'm sure that a lot of y'all have heard a good bit about over the last few days. Brief little overview, since there's already like several other talks on Ray Air. It's a really nice scalable and unified toolkit for ML applications involving each of these different use cases. And in particular, for what's relevant to this talk, is it allows you to scale from a single node to multiple nodes with basically just like a single line config change. It's basically just like, how many workers do you want for your training or batch inference workload? And then that's the extent of the change to scale up. And this talk in particular focuses on Air's data processing engine, which is a library called Ray Datasets. And it's involved in these three aspects of Ray Air. It's actually technically involved like under the hood in tuning as well. But that's just because tuning is running multiple hyperparameter tuning trials, which uses Ray Train, which uses Ray Datasets for like preprocessing and data ingest. Yeah, so Datasets is used here for all data loading. It's used as the engine for distributed and parallel preprocessing. It's used for efficient data transfer into the GPU workers for training. And it's the actual engine that performs the distributed data parallel batch inference as well. So it's used for a lot of stuff. And then one key thing to emphasize here, we were talking about how there's no shared data plane between like a Spark cluster and a TensorFlow cluster, which makes trying to transfer data between those preprocessing and training stages a little expensive. Datasets is serving as Air's in-memory distributed data bridge. So this is a shared in-memory data plane, which obviates the need for that persistence to external storage in order to exchange data between the preprocessing and training stages, or between preprocessing and batch inference stages. And so this ends up being a pretty big performance win for a couple of case studies, which we'll talk about later. So first, I've been talking about Ray Datasets in the abstract. You know, like what the heck is it? So it's a distributed data processing library, very focused on a few machine learning use cases. It's not a generic like ETL or like distributed data frame library like you might be familiar with, like Dask data frames or like Spark, for example, Spark data frames. It's very geared towards these problems of data loading, preprocessing, and ingest into trainers, and then data loading, preprocessing, and parallel batch inference. And a little bit more about what it actually is. It has a really nice, featureful, performant I/O layer, a lot of exchange with different distributed frameworks, such as Spark and Dask, very efficient exchange, and then also a lot of like performant parallel I/O integrations with your favorite file formats like JSON, CSV, Parquet, imagery, and then also very efficient data exchange with your favorite distributed training and distributed inference frameworks, such as TensorFlow, Torch, and like distributed XGBoost. The underlying compute paradigm is pretty simple. It's kind of like your famous like map-reduce paradigm. We've got basic parallel and distributed ops like map, filter, and shuffle. And with those primitives, you can express like a whole lot of different computation. And then finally, under the hood, Ray Datasets is built on top of Ray, and a Ray dataset just consists of Ray objects. So you can easily pass this Ray dataset that you've built up on your client to other Ray tasks, other Ray actors, to a Ray actor that's like your trainer. And this allows for really easy exchange of a handle to this distributed datasets data without actually having to move the data. You're basically just passing these like distributed pointers around. So that allows us to make ingest and data exchange very simple in terms of user code. So I've been talking about that there are some bottlenecks once you reach a certain data or compute scale. We probably all immediately think that the most common bottleneck is the actual distributed training, like you're having to do that very complex gradient all reduce. But there have been essentially like, hundreds, if not thousands of engineering hours devoted to systems such as like distributed data parallel torch, TensorFlow, Horvath, to make that extremely efficient. And also the accelerator interconnects between, for example, like TPUs in a TPU pod or like some of the very fast interconnects provided by your favorite cloud provider, as well as like NVIDIA's tech. You have extremely high bandwidth and extremely fast exchange when doing that gradient all reduce. And so a very common bottleneck ends up being ingest. And what I mean by ingest here is basically everything upstream from training. Your data loading, preprocessing, and then the actual data transferred to the GPU workers. So to go a little bit more into some of these ingest scaling challenges, first, you need to be able to shard the data. If you're doing distributed data parallel training, you need to be able to take a large data set, partition it into shards, and then efficiently move those shards to the trainers. You need to avoid these pesky GPU data prep stalls. If you're familiar with this, this has been getting a lot of attention in both academia and industry recently, where the chief offender for poor GPU utilization and these little GPU utilization bubbles ends up being actually ingest, your data loading and preprocessing, where you're just not able to feed the GPUs fast enough. And then finally, per-epoch shuffling is pretty difficult to do in a distributed data parallel training scenario, especially if your model is very sensitive to the quality of your data shuffle on every epoch, which we've encountered from multiple people in industry. It's tough to do in a distributed setting if you're trying to do a fully global shuffle, so we offer a few options there. Going into each of these a little bit more, data sharding, we need to be able to efficiently assign data shard partitions to each trainer, pretty straightforward. Avoiding these GPU data prep stalls, to give a little bit more color to this. If your pipeline ends up being ingest bound and you have these two stages, ingest and training, you might be basically doing data loading and preprocessing, aka ingest, while your GPU is sitting idle. And for the first epoch, it's tough to avoid that. Your GPU is going to be idle until the data loading and preprocessing is done. But then now, if you're just doing this synchronously, training and ingest entirely serially, synchronously, you are going to see that GPU idle pause, that data prep stall, on every single epoch, where your trainers are just sitting there waiting for data to be loaded, preprocessed, and transferred to the GPU workers. And this can, even if you're, when the data is actually ready and the trainers are able to actually like do training on the data, you might see 100% GPU utilization, really high GPU utilization during that batch of time. But if you're having to wait for data loading and ingest, like before the trainers can actually see the data, you might basically be seeing like an aggregate like 50% GPU utilization or worse. We've seen users actually come to us with like 20 to 30% GPU utilization, even though the training, when the data was actually available, was going pretty quickly. So yeah, that can really hurt. The idle GPUs cost money, and we don't want to burn money. Even for batch inference, although it's less of a commonly studied issue, we've also seen users that are doing the same synchronous data loading of the entire data set, pre-process the entire data set, and only then do they actually send data to the inference stage. And if you have like a large, like tens of gigabytes, hundreds of gigabytes, multi-terabyte data set, you are just burning money by letting those GPU inference workers just sit there idle. So we would really love to be able to overlap these stages to try and hide some of that ingest latency. And then finally, per-epoch shuffling. The general motivation for this is some models are shuffle sensitive, and you'll get much better model accuracy after a fixed number of epochs. This can kind of be, there's a lot of extra information on this, both in industry and also some recent research on like the convergence of stochastic gradient descent and everything, which I wish I could just spend an entire talk talking about that, because it's pretty interesting. But the general idea is per-epoch shuffling matters as well as just general data shuffling before you start training, because if you see a bad GPU batch, that can make you get stuck in a local minima when your solver is trying to optimize. Like when your solver is trying to actually like reach that global minimum, you might get stuck in a local minima. And then if you see that same batch in the same order on every single epoch, you will keep hitting that local minima. And by shuffling on every epoch, it helps you bounce out of that local minima and actually find a more optimal solution. And but unfortunately, like we would love to do fully global shuffling, fully random shuffling, as if it was like perfect, like without replacement, popping a single record at a time. But unfortunately, while that's very easy on a single node, it's hard to do in a distributed setting. And the typical solution is an all-to-all communication map-reduced style shuffle, where you mix shards, as shown in that diagram. So we've talked about these general ingest scaling challenges. How exactly does Ray Datasets meet these challenges? First, let's talk about data sharding. This is a pretty straightforward one. Basically, sharding datasets across workers using AIR and using Ray Datasets is basically a single API call. Like that's essentially it. You call .split on a dataset, and you give it the number of shards you want, and then you specify whether or not you want to guarantee that the shards are equal, in which case it will basically do like an optimized rebalancing of shards, and then it will drop like at most number of shards rows to make sure that they're equal. So it'll do a pretty like basically a minimal amount of truncating. Yeah, and under the hood, you know, it's pretty straightforward. The basic sharding algorithm, you just basically, yeah, you partition the distributed data set, and then you create a mapping from each shard to the appropriate trainer. We also have some interesting optimizations here, such as locality-aware assignment of shards to trainers. So for example, if you take the handles to the training workers, which in Ray Air and Ray Datasets, that refers to like handles to the Ray actor that is sitting on the GPU, and you give those to the split API, Datasets will then do a locality-aware assignment of those shards to those trainers. And what that looks like is, let's say this dataset already lives on your GPU nodes, and each shard is already sitting in the object store of one of these GPU nodes. All that this does is it makes sure that we assign the shard to the local trainer. And this applies even when there are like small little chunks of a shard sitting on a node. We will try to basically ensure that as much data that's already local to the trainer is assigned to that trainer shard as possible. And this really reduces data movement. If you don't have this, you could have that like for example, the blue shard in node 1 might end up being assigned to the trainer 4 on node 4, which would involve having to move that entire shard to that trainer. So this ends up really reducing data movement and actually ends up improving the ingest throughput a good bit. So next challenge, how do we avoid those pesky GPU data prep stalls? There are 3 core aspects to how we address this. First, if we speed up pre-processing, awesome, ingest is now faster, and you are able to at least decrease the amount of time your GPU is idle. If you're able to just ingest faster, then your GPUs are just going to be idle for less time, even without any fancy overlapping or pipelining. Number 2, we've got a very easy way that you can pipeline ingest with GPU compute. And then number 3, we have some options for overloading GPUs. So that involves assigning more than one batch worker to a single GPU. And then although that incurs some like CUDA kernel context switches, and that can be like a little bit inefficient, we've seen in practice that if you like overload a single GPU with 4 batch inference workers, you can typically achieve pretty good GPU utilization, like in the 90 percentile, in the 90%. So first, how do we speed up pre-processing? Few core aspects: parallel I/O and transformations. We've got all this CPU compute available across the cluster. Why don't we just do all of these data parallel transformations in parallel? Easy. First, a little background on what a Ray dataset is, a little on its actual data model. A Ray dataset is very similar to other distributed data collection abstractions you might be familiar with, such as Spark or Dask data frames. Those are like the very common ones people know. Basically, a dataset just consists of those distributed pointers that I was talking about, where it has a block reference per underlying data partition, or we call them blocks. And these blocks could actually live on a bunch of different nodes. On your client machine, all that you have is this very lightweight dataset object that just contains these distributed data pointers. And then you can very quickly do, like, orchestrate large cluster scale compute that will all be done and distributed over these blocks that live on other nodes. But like in actuality on your machine, which can even be sitting outside of the cluster using Ray Client, yeah, you're not really pulling any data to that local machine unless you actually want to. We also have a bunch of quick introspection APIs, like checking out the metadata for the data set, and then also just doing like a head call, for example, like getting the first 10 rows to make sure that everything is looking good. And how this actually translates to parallel I/O, you can probably, parallel I/O and transformations, you can probably already see how this distributed representation is nice for doing parallel operations. For example, here's like the API for reading a bunch of Parquet files from a particular directory. And that can, by the way, be in S3, Google Cloud Storage, Azure Blob Store, local disk, HDFS. We support a bunch of different storage backends. If you specify a parallelism of 2, what this will look like is if you have 4 Parquet files, we will launch 2 read tasks, and each read task will create 1 data block. And those read tasks can be executed anywhere on the cluster. And we actually have a specific optimization to make sure that data is load balanced as best as possible across the cluster for both maximal downstream parallelism and also general stability of memory-intensive operations, and I'll get to that in a little bit. But yeah, cool. Now we've got these data blocks after reading the data from storage, and these read tasks were executed in parallel across the cluster. Now let's say you then do a transformation, like a batch mapping function. So you just want to apply this function across batches, multiple batches per block. All that this amounts to is, let's say you have 4 blocks. We will launch a map task per block running somewhere on the cluster. And then within that map task, that Ray task, we will then apply your user-provided function on sub-batches, on batches of that block. And then the output is another block. So from your client-side dataset perspective, you didn't have to pull any data local or anything like that. All of these operations were run wherever the data is living in the cluster. And then basically once the computation completes, you then have handle to the new output blocks in your data set. And ultimately what this results in, instead of having synchronous single node, basically row by row or batch by batch reading and transformations, which can be slow, by parallelizing this across all of your CPU, memory, and network bandwidth in your cluster, you're able to often achieve much better reading throughput and much better pre-processing throughput just by doing this parallel execution, and that should decrease the time to arrival for GPU batches on your trainers. So we're speeding up pre-processing. That's great. And there are also a few Dataplane optimizations I want to quickly talk about. There are these particularly, once again, like improve the execution time of reading and pre-processing. The first is the load balancing of read tasks that I talked about, where we do a best effort of spreading those initial read tasks that are reading data from like external storage across the cluster. And so that should end up better utilizing the cluster's aggregate network bandwidth, and also better utilizing the cluster's like entire aggregate available object store memory, which should result in more stable pre-processing downstream. It basically prevents like those classic hot node issues, where if you scheduled all of your read tasks on a single node, totally, number one, exhaust and saturate the network bandwidth of that node, and then number two, totally max out its memory allocation. You might then, in downstream operations, encounter out-of-memory errors or a lot of spilling to disk. So that's nice. Number two, locality-aware scheduling of those transformation tasks. Core Ray will do a best effort scheduling of those map tasks to where the data already lives. So this should basically reduce like unnecessary data movement, where this is the concept of like moving compute to the data. And so this results in faster execution and less data transfer, which is basically more stable for the cluster's object store. And then finally, transparent object spilling to disk. This is more a reliability aspect of your ingestion pipeline. But I would say that the ingestion pipeline that's slowest is one that never completes because it fails. And this will prevent those classic like out-of-memory errors when you've like, oops, I've exhausted either a single node's memory or my cluster's aggregate memory. What this will do is it'll just transparently do fallback allocation to disk when first creating the object in the object store, or it will actually do like progressive spilling to disk if basically your node is currently under a good bit of memory pressure. So that basically allows you to have disk as like a less optimal but still available object store backup, and that should prevent those out-of-memory errors. So it makes data sets faster and more scalable, or faster and more stable, and ultimately it allows that preprocessing and that ingest to complete faster. So that was the first like little way that we address these data prep stalls. Number two is pipelining ingest with GPU compute. First, when it comes to training, if you remember, we previously had these issues of where preprocessing and training is happening synchronously, so you're having all of these idle GPU stalls. Now, with this very easy, basically this actually happens automatically. You don't really have to think about it as a user. But once you call .repeat on a data set, which will, by the way, repeat this data set infinitely, any downstream operations, such as random shuffling, will be pipelined with the actual training. And so what this ends up looking like is you have to take that hit for ingest for the first epoch. That's kind of unavoidable. But then as soon as you start training on the first epoch, we actually start the ingest for the second epoch. And this basically allows you to at least mitigate and at best completely eliminate those idle GPU bubbles. And so if your ingest throughput is at least as high as your training throughput, you should basically not see any of those idle GPU stalls. Your GPU trainers should only just see hot in-memory GPU batches waiting for them by the time they actually get to training on that next epoch's data. And so we've had several users that have enjoyed this feature, and this is also a very common solution in industry. For example, like a lot of your favorite Torch data loaders or like TensorFlow data sets, they typically do this like on a local scale, such that your data loading or maybe a few pre-processing operations is pipelined with like an asynchronous like background thread or background process. We actually do this in an entirely distributed fashion. And we even have a solution called disaggregated CPU and GPU compute, which means you can have a bunch of CPU workers that do all of your ingest and pre-processing, and your GPU workers are just reserved for training, and you can scale those independently. So scale your CPU workers up to meet your pre-processing demand, and then basically doing this pipelining in a distributed fashion, not just with like an asynchronous like background thread or process. This also applies for inference as well. If you remember these 3 stages for doing a batch inference, for executing a batch inference pipeline, what we can do is we can window the data set. This window call after the read will actually result in creating a windows of like disjoint subsets of the data set. So you can think of it as like chunking or windowing the data set. And all subsequent operations will then be pipelined using those disjoint windows. So as you're loading the data, for example, for the second window, you will be doing pre-processing on the first window. And then depending on the number of stages of compute that you have after the window call, in this case, we actually have that the read is transparently moved to after the window call, so that allows you to basically get fully streaming ingest. This is a double nicety of you are getting parallel execution of the loading, preprocessing, and inference stages. And then you can ultimately hope to get really good GPU saturation, but you're also like your total cluster memory utilization is kept pretty low because you're actually able to do essentially like streaming batch inference at the window level. So for example, as soon as batch inference for the first window completes, that data is then ditched. That data is released, and you can move on to the subsequent windows in the data set without having to worry about that first window taking up your cluster object store. And so this can actually be done right now down to the file level. And we are exploring even doing this down to the per batch or per row level to basically you could have like a streaming pipeline that could only just like read and process and do inference on a single row at a time if you wanted. So that could help in like super like memory limited clusters. And then finally, GPU overloading. So this is addressed in a few different ways. We've got this auto-scaling actor pool for inference, which first of all, it scales dynamically with the size of the work queue. And ultimately, that should try to ensure that your GPUs aren't wasted during inference jobs. If you've ever done like, let me statically allocate a ton of GPU inference workers, and then I'm going to hope that my work queue utilizes all of them. You can often run into the issues of, oh, oops, I overallocated by basically like 2, 3x, and ultimately I saw really poor like aggregate GPU utilization and like wasted a little bit of money. So this is a pretty common feature of like, hey, let's scale the size of the pool with the work queue. So quick little show of how this works. Let's say you start off with having a single worker in the auto-scaling pool, and then you're saying, okay, cool, I'm going to do batch inference on the first little data block. Awesome. And then concurrently, you start up the second worker because you say, oh, the work queue's decently big. I should probably scale up the pool a little bit. But starting these workers takes time. Like if you've ever tried to acquire GPU nodes from your favorite cloud provider, you can often notice like, oh boy, I don't have a lot of this particular GPU node available in this zone, or in this region, and you might be waiting for a hot second for that GPU node to become available. And then also, depending on what runtime you're using for batch inference, it can take a little bit of time to initialize that runtime. Like for Ray actors, it can take like a little bit of time to actually allocate a worker process and then start up the Ray actor. So here you have worker 2 is taking the second block. But before we can even start worker 3, we might say, oh, cool, the first block has been finished doing batch inference on it. Cool, so we can just send the third block to the first worker. And then as worker 3 starts up, we're doing this parallel batch inference on worker 1 and worker 2. Worker 3 starts, cool, that means we can take the the final block, send it to worker 3. And ultimately, that allows us to not overscale beyond the worker queue size, or beyond the work queue size, and that actually is dynamic. We're constantly looking at readjusting the size of the pool based on the amount of work that's left. Finally, we combine this auto-scaling actor pool with the pipelining of data transfers with inference and with fractional GPU requests to get that oversubscription of GPUs. And what this ultimately results in is we send multiple blocks to a single worker, which allows us to pipeline the batch inference on one block with the data transfer of the other block. And then we also might have here 2 workers that are just basically like multiplexing on top of a single GPU. And so we have 2 workers submitting concurrent work requests to that GPU. And that can usually help you saturate a GPU if your model forward pass is pretty cheap. So it's basically just multiple workers parked on a single GPU. And then finally, the last scaling challenge is per-epoch shuffling. This can be pretty difficult in a distributed setting, but Datasets has invested a good bit in a couple of really good distributed shuffling implementations. This allows for either fully global, or if you do your random shuffle after windowing, only a per window distributed shuffle. And this is just done, the first implementation is just done using a simple map-reduce shuffle. So you have a couple of blocks, you send one block to each of the blocks to a mapper, the mapper chunks that input into a chunk per reducer, and then we just basically send, each mapper sends one chunk to each reducer. The reducers concatenates those chunks and then shuffles them together at a row level. And then ultimately, at the end, we have 2 shuffled blocks, and this actually amounts to a fully global shuffle that is equivalent to like row level sampling, like perfect random sampling with replacement, or sorry, without replacement. That's the one. And then we recently added a different shuffling implementation, which is really, really cool. That actually there's a talk going on right now for this. It's the Exo Shuffle implementation, and it's a push-based shuffle. And I definitely encourage you to check out that talk. Unfortunately, since this talk is at the same time, probably going to have to look at like the virtual recording. But yeah, it's a great talk. In addition to distributed shuffling, we also have a local shuffling option. So let's say your model isn't super shuffle sensitive, like it doesn't need fully global shuffles, but you still want to have like a pretty good shuffle that doesn't really affect your pre-processing throughput so much. We have something that uses what a common industry solution, which is a local shuffle buffer. So you have a buffer of some size, some number of rows, let's say like 1 million rows, 10 million rows, 1 billion rows. And then all that this buffer does is it accumulates samples, mixes them together, and then pops off random batches from that buffer. So to give a quick little example, let's say you have a buffer size here of 4. So this is like the minimum buffer size. It must be that large before you start popping batches off. And then you have a batch size of 2. So first we add a block to the buffer, and that's going to be, a block is going to end up consisting of 4 rows. So cool, we've got 4 rows now in the buffer. Then we add another block, like cool, we've got 8 rows, awesome. Now that it's beyond that minimum size, we can start popping off those 2-row GPU batches. And so what happens is we're beyond the minimum size, time to mix up the rows, and then we pop off a batch. And then, oh, cool, we're still above the minimum buffer size, so we can actually pop off another random batch. And then so the trainer is doing training on those random batches. Now we're back like at the minimum buffer size. We can't pop off a batch without going below the minimum buffer size. So we are in the background pulling in more data to try to fill up that shuffle buffer. Cool, we're above the minimum size again, mix it up, and then pop a random batch off, pop another random batch off. But notice that these samples from these different blocks are getting mixed over time. So it's not purely like, let me take a couple of blocks from the beginning of the data set and then fully consume those as GPU batches. This is actually going to mix data throughout the entire epoch. So you're going to have samples mixed from like the start of your data set all the way to the end of your data set with some probability. So ultimately, it's still a pretty good shuffling option. And with our implementation, it's like within like 10–15% of throughput of no shuffling at all, which is a good bit better than the distributed shuffling. So yeah, this ultimately results in a trade-off between the randomness of your shuffle and the throughput of the shuffle. Finally, a few quick case studies. I know, by the way, I'm at time, so I'm going to go through this a little quickly in case y'all are hungry. We have one example is distributed training at Predabase, which I think is over there. What's up? Yeah, they found their training to be ingest bound, and their models are shuffle sensitive. So they are wanting to try and they're wanting to still try have a high quality shuffle while also being able to still saturate their GPUs. They don't want those pesky data prep stalls. So the previous solution that they had was pandas based preprocessing, then written to S3, loaded with Petastorm, and ingested into Horvath. The Ray-based solution was porting that pandas-based preprocessing to Dask on Ray, get rid of the S3 intermediate persistence, and then ingest with Ray datasets into Ray train. And they ultimately saw 8 times faster throughput, even on small data and cluster scales. And so, for example, this was one example of like the small benchmark with like a 5 gigabyte subset of the New York City taxi data set on a single instance. Even at small data scales, you see a pretty good performance improvement, and then this just gets larger at large data scales. So for example, here's one of those large data scales. We have worked with a large transport tech company, who shall for now remain nameless, that they were suffering the same issue of ingest-bound training, and their models are shuffle sensitive. Their previous solution was data was in S3, let's load it with Petastorm into Horovod. Ray's solution was still persisting to S3 because they had a large ETL job that that could run for quite a while, so they still wanted that S3 persistence. And then ingest with Ray Datasets and use Ray Train for distributed training. And the end result was that the Ray Datasets ingest was 4 times faster than Petastorm from S3. And even better, because of that high-quality shuffle, they saw approximately 1% reduction in mean absolute error. And for this model, it was actually pretty significant. And they are now looking at rolling this out to like a lot more of their internal models. And yeah, so we ultimately created a synthetic version of their data set and did basically like simulated their setup, and we got 4x improved aggregate throughput. And this is while doing a much more expensive shuffle than Petastorm was doing. This is doing a distributed all-to-all shuffle while Petastorm was just doing a local shuffle. So faster and also better shuffle quality, you know, everyone's happy. And then finally, another example from Predabase, they also used datasets for distributed batch inference. Their issue was that it was not scalable, and they were seeing a lot of idle GPUs. They were using pandas for preprocessing and then Torch for doing batch inference previously. Now they ported to Dask on Ray plus datasets and Torch for doing preprocessing and batch inference. And it was 5x faster, even on small data and cluster scales. And so here's another example on that same 5 gigabyte subset on a single instance. As you can see, Dask on Ray plus Ray Datasets is a good bit faster. There we're showing throughput. And then finally, a quick testimonial from an ML engineer that's actually using, that was using Ray Air as part of like the alpha release of Air. Primarily, they have seen a huge improvement in their developer experience. They think the abstractions such as datasets and Ray Train are super intuitive. And the big kicker was in 2 weeks, they were able to recreate and outperform a data ingest pipeline that they had built bespoke by hand over the course of 6 months. So you're seeing an improvement in developer UX, the time to actually deliver a solution. It's really quick to try out. It's pretty quick to port most like existing solutions to Air and datasets. And yeah, and they achieved better performance than their existing solution. So reduction of tech debt, reduction of time to ingest. Everyone's, once again, hopefully pretty happy. And so a quick summary, wrap up of the talk. Scaling ML pipelines is hard. Ray Air makes it pretty simple. Ingest is a common bottleneck as data volume scales, in particular leading to idle GPUs. And then Ray Air uses datasets to fix a few of these problems with features such as distributed data sharding, fast I/O and preprocessing, smart and resilient data plane, and then finally pipelining of CPU and GPU compute. Oh yeah, and also efficient and scalable per-epoch shuffling. Can't forget that one. And yeah, so this is a quick teaser for ongoing and future work. We're planning to work or actively working on all these things. A few that I would call out is faster tabular preprocessing with distributed polars. I saw a 20x improvement over using Arrow as the compute engine for example, for group by and aggregations. By switching to polars, I saw a 20x improvement in throughput on a bunch of different data scales, which is exciting. Hoping to get that merged soon. We're going to be adding support for joins, for NLP and CV preprocessors, looking at data connectors, looking at supporting elastic training, graph neural network training, like pipelining device transfers, as well as the rest of preprocessing. And then finally, we're looking at an automatic ML pipeline optimization, aka like a query pipeline for your entire end-to-end ML pipeline. Thank you. That was my talk. And yeah, I'm happy to stick around, answer questions, or we can talk outside. But I won't blame you if you want to go get lunch. I know this went a little over. But thank you.